Hello, welcome to another video. This one will go over the elements and how we identify them. An element is defined by its number of protons. Change Z, change the element. An important note is that in a neutral element, the number of protons is always equal to the number of electrons. Now the mass number, A, counts protons plus neutrons. So different neutron counts give isotopes like carbon-12, carbon-13, and carbon-14. Ions are just atoms that lost or gained electrons, like sodium becoming Na plus and chlorine becoming Cl minus, which is how table salt happens and why chemistry tastes like fries. So Z refers to the number of protons. A refers to the atomic mass. Isotopes are variations of elements in the periodic table, but with extra or less neutrons. So examples are, so I'll just put variations of number of neutrons. And ions are when an element loses or gains an electron. Now electrons don't orbit anywhere they please. Quantum mechanics gives them quantized energy levels, and the Pauli exclusion principle says two electrons can't share the same state. These rules create shells and subshells, and we label them as S, P, D, and F. And set valence electrons, the outer ones, control how elements bond. So shells and subshells can be labeled as S, P, D, F. And the Pauli exclusion principle basically says no double parking. And this is where the idea of an electron spin comes into place. The periodic table arranges elements so rows, also known as periods, show shelves filling across columns, also known as groups, line up similar valence patterns. Hence, fluorine, chlorine, and iodine act alike because they lie on the same column. You can predict trends. Atoms generally shrink across a row. Ionization energy rises across a row. And electronegativity, how hard an atom pulls shared electrons, follows patterns you can test. Why trust this map? What I mean by map is the periodic table. Mendeleev predicted missing elements by leaving gaps. Moseley used X-ray spectra to tie atomic number to nuclear charge. And modern quantum calculations reproduce shells and trends that match lab measurements in astronomical spectra. Cecilia Payne showed from stellar spectra that stars are mostly hydrogen and helium when many assumed they were like Earth. And she was right because the lines matched atomic physics, not preference. Meghnad Saha's ionization equation links temperature and pressure to how ionized a gas is, which explains how hot stars show different lines than cool stars. Margaret Burbidge connected stellar processes to the table's elements, and Henrietta Leavitt's period luminosity law for Cepheid stars let us place those element factories in three-dimensional space. This is a chain of evidence where predictions meet measurements and either stand up or get rewritten. Spectroscopy is reading light's fingerprints. Each element's electrons absorb or emit specific photon energy, and conservation of energy guarantees that photon's energy matches the electron's jump up or down, the different energy levels, which are referred to as these letters. We reproduce those fingerprints in labs and then match them in starlight. So when we say there's sodium there, it's because sodium literally signed the spectrum. So for spectra, so spectra lines basically match the energy, the photon energy jumps. And what we see in the lab matches what we see in stars. Astronomers call everything heavier than helium metals, as we discussed before. And the star's metallicity, its metal content, is read from those lines and correlates with the likelihood of a rocky planet. Carbon's four strong bonds enable complex molecules. Oxygen's electron hunger powers respiration. And silicon builds rocks and microchips. Yes, the periodic table runs your body and your phone. When chemists talk about exothermic reactions releasing heat, that's still conservation of energy. Stored energy in bonds transforms into heat and light and sometimes motion. The same bookkeeping applies from lab beakers to stellar cores. Energy doesn't vanish, it swaps pockets. If the periodic table looks like a bingo card, it's because nature really likes patterns. Lucky for us, those patterns are predictable and testable rather than free space. Let's inspect an image of hydrogen spectra from our own sun. Hello. I wanted to take a moment to talk about spectroscopy just briefly. Spectroscopy allows us to learn about objects that are far away and about the light that emits from objects that is invisible to our naked eye. Visible light, which is what you see here, is electromagnetic radiation that has a wavelength between 400 nanometers and 780 nanometers. Nanometers meaning 10 times 10 to the power of negative 9 meters. In the light of the sun, all of these wavelengths occur. Normally, sunlight is perceived as white, but if you fan out the sunlight according to wavelength by a prism, then the rainbow colors of the spectrum become visible. Now, what you're seeing here is the first line or spectra on the top is all the spectra that's visible to the human eye. If you look at the one in the middle, this is the absorption spectrum of the element hydrogen. So This middle is if we just isolate hydrogen and we are able to absorb the spectra, then we would see these little black lines appear as you see them right there. Now, it's important to note that there is a relationship between the energy or the wavelength of light in those black lines and quantum mechanics, which is really to say that these at these wavelengths, at these energies of light, is when electrons shift. Because remember, electrons have discrete energy levels, so the energy is also discrete, and energy is released in the form of light. Now, if we look at the spectral lines of the sun, we can see that there's a lot more lines than the ones for hydrogen. So a couple things here. Well, first you could see that all the lines in the absorption spectra of the element hydrogen are in the sun, in the spectral lines of the sun. Now, there are more lines because the sun has a little bit of helium, and technically the sun also has some carbon and nitrogen and oxygen. Very small traces, but nevertheless. So we can see the spectral lines of the sun are more than the absorption spectrum of hydrogen. So this is what scientists can do. Scientists can look out or look at a piece of material, figure out the spectral lines coming from that material, in this case the sun, and then we can line up these little dashes with the absorption spectrum of elements that are here on Earth. And by accounting which lines are there for the sun or any other given object, we can determine what things are made up of. Now, this is important because a good question is, how do we know what things are made up of? Well, spectral lines. We understand quantum mechanics. We understand how light is emitted from substances. So using that knowledge that here in the lab we can replicate, and maybe some of you have seen this at some point in your life. It's very common in chemistry, for example, that you actually get the demonstration of this yourself. But basically, we're able to match the observations in the lab with the observations outside of the lab and get to concrete answers that we can be confident in. Now, spectroscopy and spectroscopes is a whole nother topic. There's a lot of history, there's a lot of things I could say, but I just wanted for everyone to see just the most basic way of explaining this, which is hydrogen, which is the most basic element that exists, just has one proton, one electron. And of course, relating that to the sun, which is where all our energy comes from. And one final note is that here I'm just talking about the spectra of visible light. But of course, there are many, many different kinds of light. And the vast majority of the kinds of light are actually not visible light. We will talk more about light in a future video. Quick recap. Elements are set by proton number Z, isotopes by neutron number, and ions by electron trades. And the periodic table organizes repeating behaviors because electrons sit in quantum-defined shells that control bonding. We trust the table because Mendeleev predicted gaps. Moseley tied atomic number to X-ray spectra in quantum theory, plus lab data and stellar spectra all agree. Spectroscopy works because electron jumps must conserve energy. So photon energies match exact differences, and we can identify labs and elements in labs, stars, and nebulae. Astronomers measure metallicity from those lines, which connects starlight to the odds of rocky planets and to the chemistry of life and technology. The story's builders include Payne, Saha, Burbidge, and Leavitt, showing how diverse, testable contributions make the map reality. From salt on fries, to oxygen in lungs, to silicon in chips. The periodic table is where quantum rules meet everyday life. Thank you for watching. Hope to see you next time.